Okay, so let's start. So let me welcome Travis Schedler, who will tell us about D modules on Poisson varieties.
So I want to thank the organizers very much for your hard work for putting together this conference and for the privilege to me to be able to speak at this event in honor of some mathematicians who have greatly inspired me.
We need, let's just say recorded, so we need the microphone.
Someone record?
The microphone Robin's replacing the batteries on it.
Okay.
So there will be a microphone soon. So anyway, since Andre wasn't here, I wanted to thank the organizers for the opportunity to speak here in honor of the two mathematicians who inspired me and have helped me a lot. And unlike Ed Frankel, I cannot say that I've known Pavel for 33 years, but I have known him for over half of my life. And it's been a good half. And in fact, I've known him since a high school research program where Pavel infected me with the excitement of math research. I saw a problem which seemed very difficult the previous day melt away due to some new connections that we had to discuss and Pavel had to explain to me. And this particular problem actually infected many others. So I still continue to get emails from the research team that have reminded me of this fact. And even Pavel says that it's one of his most cited papers. So I guess that's a strong statement. Pavel also went on to have many other such successes with other high school students over the years. And so he's very talented at this. And for my part, I have had the great privilege and fortune to have had many other exciting moments of my own, but they're never the same without Pavel. So it's really great to have this privilege to work with him. And I just wanted to say happy birthday to Pavel and Andre. All right, so I have to speak about mathematics too. So this is a project which I've been working on with Pavel Eddinghoff for many years. And so I apologize to many of you who have seen me speak about it many times already, but there are still new developments. And so I wanted to tell you more about it. So I will begin speaking a bit about Poisson Co Homology. So X is an algebraic variety. So we're just going to work over C, and it's Poisson. So I assume at this conference most of you have heard of this before, but just very quickly, it means that OX has a Lie bracket. So this is the Lie bracket. And for a function, this bracketing with a function is a derivation, or in other words, a vector field. So this is going to be a vector field on X. So this is what a Poisson structure is, and just as a reminder, so that of course the first and most important example is if X is symplectic. And there's a unique Poisson structure defined by the formula that if you contract with this, so the vector field is defined by the formula that contracting with it gives you dx. This defines that guy, and therefore the bracket. So that's this is one way of thinking about a symplectic structure. And we can also do something more interesting on that, which explains why this is a useful notion. you can take a group acting symplectically. So let's make this a finite group acting symplectically. You can do this also for infinite groups, and actually Hiraku Nakajima, he did this in his talk. But let me just say for the finite case, then we get a quotient x mod g is Poisson. So it's not going to be symplectic in general because this group doesn't have to act freely. So this will be singular in general. But it will still be Poisson, and the bracket is just the same, so locally. So if we were affine, then we just restrict this bracket to functions, to G-invariant functions. So if x were affine, it would just be the restriction. So this is very useful notion. So you can think of Poisson structures as a sort of degenerate or singular version of symplectic or generalization. So you also, maybe I should give one more example, which I'm going to mention a little bit more later. On the projective space, this is not a symplectic variety. So in particular, if you were symplectic, you would have to have a non-vanishing holomorphic volume form, and this doesn't have one. But it has many interesting Poisson structures. So Fagan, Berlinski, for example, define some elliptic Poisson structures. And if you quantize them, so already this has been mentioned at another talk, so Poisson structures, the other way in which they arise, aside from symplectic, is by starting with something non-commutative and taking a limit. Or conversely, if you have some Poisson structure, you can quantize it, you can make a non-commutative deformation out of it, and this bracket here is telling you the first order part of the commutator, AB minus BA. So if you quantize this, you get these elliptic algebras. And these are homogeneous. Homogeneous algebras. Okay, so let me say more about that later. Now what I want to do is I want to tell you what Poisson Co Homology is. So if X is smooth, you can take this Lichner-Rovitz complex okay, and you have a differential. This differential D is not O linear. It's actually a derivation. So if you apply the differential to just a function, you get this vector field we had here. And if you apply it to a vector field, you get the failure for the vector field to be a derivation of the Lie bracket. In general, D of something. In general, D of something is equal to the Schouten-Nienhaus bracket with this sigma. So if you've seen this before, this is the Poisson bivector. So because this is a derivation in both components, it's associated to a bivector, and you can, and it's skew symmetric. So it's del square. It's the exterior square of Tx. So if you this Schouten-Nienhaus bracket is just an extension of the Lie bracket, also to be a graded derivation. Okay, but you don't need to know the formula here. Just if you haven't seen this before, just bear in mind this is a derivation. So it's not O linear. So it has interesting interpretation. So H0. So let's just say, for simplicity, so if X is affine and smooth, then H0 of this L, which is also called the zeroth Poisson cohomology, is just going to give the what are called the Casimirs. So the functions that are central right? And then and H1, which will be the first Poisson cohomology, will be the derivations of the bracket modulo the Hamiltonian ones, etc. But HP2 is somehow the most important one from my point of view. This is governing classical deformations. So deformations in the ordinary sense of you have another Poisson structure which deforms the original one, or maybe you deform the variety as well. And for general X, it's a similar story, but we have to take hypercohomology. And you can also do a similar story for the Poisson homology, but let me just say I only need one formula for it. So if X is affine, I only actually need, so it's amazing that a lot of my work with Pavel has to do with, or work that was inspired by Pavel has to do with the zeroth homology of something. So a lot of our work is just about only the zeroth homology. And so, sometimes what seem like the simplest things actually have a lot of beautiful mathematics behind it. So HP0 of X will be, if X is affine, it'll just be the functions modulo brackets. And by that I mean the linear span of the brackets. Okay. Right. So now let me say what this is good for. Well, I said it already. If you want to understand the deformation theory, and also if you want to understand the quantizations, then this HP, this cohomology is very relevant, especially the second. And if you want to understand, this guy is going to be related to the representation theory of the quantizations, because this space is related to traces. So let me just write this very briefly. HP0 of X is related to traces. And HH0 of a quantization. So A is a non-commutative algebra. This is A mod brackets. And if you have a representation, and this implies that the trace of rho in V is finite dimensional. Trace of rho is a function on this guy. So as a result of all of this, we get that by character theory, so by some Wedderburn theory, etc., we get that the number of irreducible finite dimensional irreps of every quantization, that is non-commutative deformation of X, is less than or equal to this dimension. So this is why we are motivated by this.
I have a question.
Yeah?
How is HP2 related to second homology?
There's a spectral sequence that relates the Poisson cohomology to the Hochschild cohomology. It's called the Berlinski spectral sequence, I believe. So the point is that what you want to think of, if you're thinking of A as a deformation of O of X, then let's say it's filtered, then you, if you take associated graded of the Hochschild, then you have a map from that to the Poisson. So on the zeroth level, it's just a surjection. But on the, I'm sorry, it's the other way. The zeroth level, so in 0, you have HP0 of X surjecting onto GER of HH0 of A for A filtered quantization. But if you want to look at the higher homology or cohomology, there's a spectral sequence relating them. Okay? Any other question? Right. So this is an easy exercise, by the way, to see that you get this if you have a filtered quantization. You have to assume that it's non-negatively graded. Okay. So what I wanted to say is so let me give some example of what happens with this theory. So 1 is X smooth affine and symplectic. Then we have an isomorphism to the top cohomology, where you take a class and map it to F times the volume form, which in this case is dim X over 2. So this is a symplectic volume. Okay, so you take an element in here modulo Poisson brackets, and you'll see that the cohomology class doesn't depend on the cohomology class of a Poisson bracket will be 0 when you multiply it by the volume. And you get this isomorphism. More generally, we actually get an isomorphism. You can identify the Theorem complex with the Poisson complex, with the Lichtner-Ovitz complex in this case, and you get an isomorphism like that. This is also isomorphic to the homology with the degree is inverted. You can do the Theorem cohomology here. And so, as a consequence, one way to think of this as a consequence, although you can see this also without using this theory, is that the deformations are governed by H2 of X. So it's just to form the symplectic form, so an infinitesimal deformation. Infinitesimal. We just take the symplectic form and we replace it by T times omega prime, where omega prime is a closed 2 form. So let's say mod T squared. So all the infinitesimal deformations up to equivalence are given by the second cohomology in this way. So when X is not affine, the situation becomes slightly more complex, but it's still true that the deformation theory, properly formulated, is governed by the second cohomology. Now I'm ready to say some things which are not. So this was sort of all background, I guess. And let me try to say something which is a little bit different. But first of all, I need one more example. So I'm going to do it. I want to do a singular example as well. One more example. We're going to take X is C2 mod a finite group. So the simplest type of quotient we could take, C2 mod a cyclic group. And so this is spec. So this is a very explicit example. You have functions in 2 variables which are invariant under the cyclic group, so they're polynomials in these 3 variables. Well, they're the polynomials in 2 variables you get that are generated by these 3. And so in this case, an easy computation could be an exercise is that HP0 of X as basis is given by 1 xy up to xm minus 2 y to the m minus 2. So it's m minus 1 dimensional. And so what we get is that HP0 of X is isomorphic to H2 of the minimal resolution. It's a minimal resolution. Since it's 2-dimensional, it's the minimal resolution. This is also symplectic. So it's symplectic. And there was an old conjecture that Pavel and I had, which is now disproved. So it's a disproved conjecture. It was disproved by actually one of Ivan Los's students, Schwelechowski. So anyway, disproved conjecture said that, but it was proved in many cases, says that HP0 of x is isomorphic to H, the top cohomology of a resolution, for x tilde, a symplectic resolution. So it's disproved. It was disproved for a quiver variety with 2 loops. But it's proved, so it's true for all the known finite linear quotients. So of course this includes things like Hilbert's scheme of a resolution of a Duval singularity. And was proved also for toric hyperkähler. And for the nil cone, so Springer resolution, and slices of them. So this is where we were at, and optimistically, so an optimistic conjecture would be that it's still true for quiver varieties without loops. So it seems like this should be able to hold, but yes, probably, yeah. Yes, that's true, yeah. Although if you're doing if your group is not if you have a non-trivial group in here, then you don't need a loop. But yes. If you're trivial, then you have a loop. Yeah. So you can have one loop. Although I'm not going to write that on the board. So already this is optimistic, so I don't want to make it any stronger. Yes, this is what happens. So the left-hand side is always going to be bigger, I think, in these cases. So what happens is, if you have a cone, this guy can never be 0, because brackets are all contained in the augmentation ideal functions at the vertex. But it does happen in this example that the exceptional fiber, or the fiber over the vertex, is not Lagrangian. It has smaller dimension. So the cohomology here is 0. So yeah, I think this is what happens in general when it doesn't hold. That actually, probably you can prove this too. That the only thing that can happen is this guy can jump. I think you can prove this. Yeah, I think this may be true actually.
But that follows from what you said before.
Yeah, this is.
That's right. Yeah, but I don't think this is proved in general. So I mean, I think another way to try to correct this statement, other than restricting the x, is to form a quantum version, and I think this might have a chance of being true in general.
I think isn't that known? For generic parameters.
Yes, for generic parameters, I guess. Right, for generic parameters, this is no problem, because for generic parameters, it's because you have a generic smoothing, which is affine symplectic. So for generic parameters, you can prove this. But yeah, I think you can formulate a stronger statement, which is for all parameters, but I won't say how to do that. Okay, and that may be true. All right, so let me say a little bit more about why this is useful or interesting before I move on to D modules. But I need to keep track of the time here, so I've been going really slowly. But let me just say very briefly, this is interesting because HP0 of x is graded if x is a cone. So in most of these examples of interest that I wrote, all these examples of interest that I wrote on the board, x is a cone. So you have this additional grading. And with what I'm going to say about D modules, using D modules, we can actually get a bi-grading not just on not just on the top cohomology here, but on all of the cohomology. If the false conjecture actually holds, right? But in many of these cases, it does, and so you get a bi-grading, and then if you take the Poincaré polynomial, the Hilbert-Poincaré polynomial, we get interesting polynomials. So we get so in the Springer case, we get Koska polynomials appearing. So the bi-graded polynomial, so two variables x and y for the two gradings, you're going to get for the Springer resolution, you're going to get a sum over irrep, so the Weil group.
Sorry, Davis.
Yeah?
So in your disproved conjecture, it's on the top homology of x still appears.
Well, actually, you can make a stronger statement for all the cohomology, but I only stated it for this one. But it's already disproved there, yeah. But actually,
in good cases, still you.
Yeah, in good cases,
statement.
yes. So I expect that this statement is true in many cases. So it's true for these cases, and I'm optimistically saying maybe quiver varieties without loops, and probably
In those
other
cases.
cases.
It's also the full cohomologies.
Yes, you can formulate a stronger statement, which I didn't state. But so there's a way to enhance this to a stronger statement that gets all of the cohomology. In particular, it gives you a bi-grading on all of the cohomology if you started with a cone. And I expect that this statement will hold. But actually, we proved a statement at some point that says that it's enough to prove this statement only as long as you do it for all of the symplectic leaves. So if you prove this for slices to every symplectic leaf, then you get the stronger statement. I proved this with Nick Proudfoot. Okay, so Koska polynomials appear here. This was a formula that George Lustig suggested to us many years ago, and I proved this with Gwyn Bellamy, that you get this polynomial out of that. And in the toric hyperkähler case, you can get Tott polynomials, or more precisely, there's a multivariable generalization of this defined by Denham, which is what you really get here. But Tott is related to Tott polynomials, actually Denham polynomials. And you can compute what you get in other cases, and then the conjecture, again with Pavel, is that for quiver varieties, at least for the conjecture holds, for quiver varieties, if the false conjecture holds, then we get these Lustig's Q-weight multiplicities. So actually, I think there's a way, even if the conjecture doesn't hold, I think there's a way again to correct it. But anyway, this statement here is best for no loops in your quiver anyway, if you want to talk about Q-weight multiplicities in the usual sense. Factorization, I'm sorry.
You wrote the form, on the left, you wrote the formula for the Poisson case. So you wrote that now, first we have something which depends on two variables x and y, but it depends on the two variables in a very specific way.
Oh yes, that's right, yeah.
So is that what we also expect?
Well, yeah, well, there's a reason for that because Yeah. Well, the point is that if you take your symplectic resolution, you can if you think of the symplectic resolution, instead of taking its cohomology, you take the integral down under the resolution. So you take the push forward of the canonical D module under the resolution, and you can decompose this along the symplectic leaves, and this has to do with this decomposition here. But for this conjecture here, you can think of that just as the top cohomology. So that's the part that lives over just the point of the cone, the vertex.
So do you mean by grading on associated graded of h of x tilde?
Well, according to this isomorphism, you get a bi-grading. But what you really, more canonically, is a filtration. So canonically, so there were two problems with this conjecture, actually. One problem was that it was false, which we didn't know for many years. But before we found out it was false, that we realized quite early on that this is a non-canonical isomorphism. Canonical. So there's a fix for hopefully everything, but we had a fix for the non-canonical aspect.
So isomorphism that doesn't exist is non-canonical.
Yeah, neither exists nor is canonical, but in many cases it exists, and you can form a canonical version of the isomorphism. So canonically, since I'm going very slowly, I won't say too much, but you can define a filtration for every one parameter smoothing. So we're going to take our resolution and I'm going to replace it by a deformed version. For every one parameter smoothing, we can define a filtration on, let's say, the cohomology of the fiber at 1. So this smoothing, it's going to be, so we're going to call this rho t, and the rho t is an isomorphism for t not equal to 0, and of course it's our original resolution, symplectic resolution for t equal to 0. And xt, these are all affine. So you can think of it either as a smoothing of your base, or you can think of it as an affinization, well, not an affine deformation, of your resolution. So you get a filtration on this cohomology. It's just by order of vanishing. So since this is affine and smooth, you can represent the cohomology classes by some global forms. You can take a global form that represents this class, and you can extend it to a form that's fiber-wise closed of the whole family. And you consider the vanishing of this so if you extend it to a form on the whole family, then you look at its vanishing in the cohomology at 0. Because of course the cohomology at 0 is not generated by global forms. So you can extend this to a global form and see to what order, as t goes to 0, it vanishes here. Okay. So as t goes to 0. So as t goes to 0, and we're taking, we're really taking x tilde t as t goes to 0 to make this order of vanishing precise. Okay, so this is a way to define a filtration. So the canonical thing is that the associated gradient of this filtration should give you this bi-gradient. But this is actually a conjecture that it gives you the same thing. Let me write that. So I just want to say that as a conjecture of Eddinghoff and myself, is that the associated graded of this cohomology in cases where the false statement holds, the false conjecture holds, recovers this Poisson, this thing that we call the Poisson de Ram homology of X, which I didn't define. So I'm going to tell you how to define it now. All right, but you can also think of this as a correction to the false statement, because you can always define this filtration. You can ask whether this recovers these interesting polynomials, like the Q weight multiplicities. That's an interesting question you can ask regardless of whether you know this false conjecture. Okay, so let me move on now. I've used a lot of time, so I have to say a little bit about how to prove something about this Poisson homology, which also explains how to construct this guy up here. So let me say something about D modules. So for this complex L, again, as I said, D is a derivation, which in particular is a differential operator. So we can form this thing which is differential operators from O to L together with a post-composition by this differential. And now this is a complex of D modules of differential operators on O or dx modules. So again, whenever I talk about this complex like this, x is smooth. Actually, if x is not smooth, you can try to replace this complex by something else. Like you can take the tangent complex instead of the tangent sheaf. Okay, so we get this this complex of D modules, and now the Poisson Co homology is just going to be the push forward to a point. So let's call this guy mx co for co homology. So we're going to have this mx co for pi, the projection to a point. This is so this guy is a D module functor for pushing forward to a point, but it's just tensoring with O. This was a complex of right D modules. So if you tensor back by O, you get back. This is what's called the Theorem functor. You get back your original complex. And you can do a similar thing for homology. So similarly, we can, for homology, we can define just a single D module. You can also define a complex here, but let me just define instead its sort of truncation to just a single D module. So for ham x, it's the Hamiltonian vector fields. So there's just a couple words about this dx. Now, this dx is this right D module on x. So if x is smooth, it's just the differential operators. But in general, you have to be more careful how you define D modules on something singular. You can define this guy, and it has a left action by vector fields. And hom of D modules from dx to blank is the global sections functor. There's this canonical thing you can define that has these properties. And by the way, I have a student who is working on this. So Hai-Ping Ying, who's here, is working on, in some cases, showing this dx is a compact generator of the derived category of D modules. Let's say if X is a locally complete intersection in affine. Otherwise, you have to do a little bit more. But so you can use this to rewrite your D modules as modules over some ring of differential, some DG ring. Using that. You can also use this to give some more explicit formulas for things like the inverse image under a closed embedding of something singular. Anyway, so you have this guy, and you can define this D module, and now again, pi star of mx is going to be, if we just take the zeroth cohomology, this will be hp0 of x if x is affine. So it's just literally going to be mx tensored. You can really think of it as this, which is just OX modded out by brackets, because you're applying Hamilton vector fields. So you have to be a little bit more precise. This formula really only makes sense in that smooth case, but you can make sense of this formula. Okay, so you can define these D modules. And what is gained by doing that? What's gained is that this gives you a local version of Poisson Co Homology. We already had a local version, which was this this sheaf with its definition. But this gives you, allows you to apply the powerful tools of D modules. So why is that useful? So as a consequence, if this mx co or mx is holonomic or has holonomic cohomology, this is a notion of smallness. This is a smallness property. And this implies, by the theory of D modules, that this push forward is also holonomic. Under any map, let's say just to f star, and for f equal to pi, going from x to point, well, holonomic on a point is just a finite dimensional finite dimensional vector space. So we conclude, corollary, so if it's holonomic, and this implies that the Poisson cohomology of x, or this zeroth Poisson homology of x, is finite dimensional. Okay? And I want to say that smallness is something you can really check. It's saying that it says that the characteristic variety is Lagrangian. So inside of T star, the cotangent bundle is Lagrangian. So if you were working on something smooth, this would be saying that your characteristic variety is Lagrangian. Here, x will be embedded into V smooth. So if you want to think about it on some ambient smooth space, so you can really check this locally. So what is the results that you get out of this? What you get are the following things. Right. So now I get to applications. So I have a theorem with heading off. I think we proved this back in 2009, if I'm not mistaken, is that if x has finitely many symplectic leaves, which means orbits under this Hamiltonian flow, all these vector fields, then this HP0 x is finite dimensional. In particular, this recovers a result with Berest heading off Ginzburg, that if you take the Poisson homology of, say, a linear quotient, this is finite dimensional. Poisson homology here, where gamma is a finite subgroup of the symplectic group.
So, Master, in this project, are your students difficult part is to show it's a generator or that it's compact.
Well, under the LCI condition, it's pretty easy to show it's compact. And showing it's a generator is also not that difficult. So actually showing it's a compact generator itself is not that difficult, but it's more a question of trying to make sure that we've understood the relationship between the different definitions of D module and then computing this in some cases. So in particular, you can use this to get some explicit formulas, which I'm not sure were studied before. So, you know, I'd be happy to speak more if any of you are interested, but it's just sort of little technical issues about different notions of generator, different notions of, you can take derived category of D modules supported on a subvariety, or you can take the derived category of all D modules with the cohomology supported on the variety and stuff, so just dealing with these sorts of issues. All right, so applications, we have that, and as a result, so these things called symplectic reflection algebras, defined by Eddinghoff and Ginsberg, have finitely many irreducible finite dimensional representations. We have to do a little bit more work than that here, because literally the quantization of this guy is what's called a spherical symplectic reflection algebra, but you can extend this result to the full symplectic reflection algebra. So this was kind of an application. So similarly, with PIM, Rent PIM, if you use the complex, then the same result should hold for the ordinary Poisson cohomology and homologies. But to do this, since this is really only interesting if X is singular, because otherwise if you have finitely many leaves, so it's a nice exercise. If you have finitely many leaves and you're smooth, then you're just symplectic. This is only interesting if X is singular, and so you have to use the tangent complex. So we haven't written this down yet. But so the idea of both proofs, so if X is a union of some leaves, let's call it Li equals a symplectic leaves, then if you take this D module, you can just you can see that the equations that define a D module, or in the case of a complex, you can find a homotopy, which says that you get equations on the characteristic variety. So this lives inside of the union of the conormal bundles. Well, so we want to be precise here. So precisely. So unless you're, so the way that we do D modules in this series of work is we think of X sitting inside of a smooth variety. And you think of the M as a D module on V. And then we get that the characteristic variety lives inside of the conormal bundles inside of V. But anyway, the point is that these are Lagrangian. So conormal bundles are Lagrangian. So this implies that Mx is holonomic. So in the theorem 2, you have to define a homotopy on the complex so that it shows that multiplication by the equations cutting out the conormal bundles X by 0 on the cohomology. At least after taking associated graded. Okay, so that's sort of some applications. Finiteness, and again, in each of these cases, we get finitely many. So theorem 1 implies finitely many finite dimensional irreps of quantizations of X And theorem 2, of course, implies that you have a finite deformation theory. Because as I said, the Poisson Co Homology governs a deformation theory. So let me give some practical consequence of this. By practical, I mean computational. So when you're working with Pavel Eddinghoff, he's somebody who really likes to have concrete numbers and concrete computations to deal with. So that's actually something I really like as well. I like, not just having abstract statements, but really being able to see how they work and give you something really exciting.
Well, it's because if I think only about abstract statement, I get things wrong all the time.
Well, I have this problem even if I am doing concrete things, so unfortunately. So I have to check for errors. Anyway, so Theorem 3, some more specific applications of this with Brent Pym. So if, actually, this is actually an extension of the theorem I wrote. So if X actually has finitely many modular leaves, and let's just let X be smooth here, because we've only proved things when X is smooth, only written them down. X is smooth. If finite modular leaves, then this cohomology is finite dimensional. Or more precisely, the stalks of this complex are finite dimensional cohomology. Cohomology stalks are finite dimensional, to be more precise.
What are modular leaves?
So a modular leaf, I wanted to say that. So a modular leaf is larger than the symplectic leaf. It goes orbit under the Hamiltonian vector fields plus a modular vector field, where zeta, it's the Hamiltonian of log g, where locally the degenerate locus, so the degenerate locus, which is the vanishing of the top power of this Poisson bivector. So you take the vanishing of this guy, locally this degenerate locus is given by the equation g equals 0. So then you can take the Hamiltonian of its logarithm. This is called the modular vector field. This was defined by Weinstein, I believe, and Zuckerman, I believe, also. So you get this guy. So this is bigger. So this actually can be relevant in many cases. So corollary, if we take P2n and we take this Fagan-Odesky structure, Fagan-Odesky.
What's
G
G?
is equation, say, cutting out the degeneracy locus.
And sorry, I mean, so X here is R. What is the assumption for X in these theorems?
And which theorem?
Like theorem 2, for example.
Well, the theorem, its progress would be just that X has finitely many symplectic leaves. That's theorem 2.
And HP dot of X?
This would be the ordinary Poisson cohomology. I'm sorry, in each degree. Sorry, in each degree. Thank you.
Aha, so you have such theorem.
Yeah, not the whole thing, because of course I forgot to say this. If you're singular, then in general it will almost always be true that you'll have non-zero cohomologies in almost every degree, or at least infinitely many degrees. But what we can prove is that this complex may have infinitely many cohomologies, but they're holonomic. So as a result, you get finite dimensional cohomology in each degree. But we haven't written this down. Sorry. Okay, so for this Fagan-Odesky structure, there's finitely many modular leaves. So we were able to compute its H2. So we're able to, with a computation, to prove that HP2 is two-dimensional. which implies that the universal deformation is by varying these two parameters, by varying E and zeta. So E is an elliptic curve. It's the vanishing locus of the Poisson structure, and zeta is a vector field on it.
Just a second. So, first of all, here I also want to say HPI of X is finite dimension, right? Or all.
Well, if you're smooth, then you have only finitely many.
Finitely many.
But this should generalize also to the non-smooth case. But since we haven't even written the theorem 2, I thought I would just write what we've actually established.
Sure. Why is there only one modulus of deformation for this elliptic curve?
There's elliptic curve. Oh, why is there only one? Well, it's a normally embedded elliptic curve. So I don't remember exactly why this is now, but yeah, there's only one modulus up to automorphisms of this. Well,
you can move the curve itself. You can move the line bundle.
It's really the modulus of the curve itself.
But can't you move line bundle to the same degree?
But then that's pulling back for a translation.
The point is that.
Think of it as an elliptic curve. Think of it as a genus 1 curve. That's what it really is. So it's a genus 1 curve embedded in this projective space, and so that's sort of one modulus. You only have one line bundle on the curve, so it's a one-dimensional one. It's a one-dimensional stack.
Okay, so I don't remember precisely the details about this, but it turns out that up to equivalence, up to automorphisms of your P2n, it's just the modulus of the elliptic curve that matters.
So elliptic algebras give rise to such things when you have finitely many modular leaves, yeah?
Yes, exactly. So as a matter of fact, you will not always have finitely many modular leaves. So for these ones, Q21, 1, these have finitely many modular leaves. But the other Fagon-Odesky ones, Q2n plus 1, 2, 3, etc., they don't always have finitely many modular leaves. But it looks like it could still be true that they're holonomic and we get finite dimensional cohomology. So this is not an if and only if. This is just an if. So
Right.
let me write the converse.
But no statement about homology, only cohomology, yes?
So for homology, you need to have finite many symplectic leaves.
Ah.
So the point is, I got derailed by trying to say too much. So now I'm probably out of time, but let me just try to explain briefly what has happened here. I wanted to also give you one more example. So what it is that has really happened here. So just a few comments. So first of all, optimistic conjecture. So this would be with PIM, and we also we now are working with another student, a former student of Marco Gualtieri Matchevuk.
So you have a paper already, like Theorem 3, is it published already?
This is published, yes,
Uh-huh.
for X smooth, only for X smooth. So optimistic conjecture is that so this MX cohomology, so X is smooth again.
So if you have coadjoint representation of two-dimensional non-abelian Lie algebra, does it have finitely many modular leaves?
For a Lie algebra, you're saying?
Right.
Most Lie algebras, no. There are very few that would
No,
have.
just two-dimensional one.
A two-dimensional one, yes, I guess that's right. Yeah.
So the symplectic leaves, there is a line of points, and then there's
Yeah.
everything else.
Yeah, that's right.
This
Yeah.
vector field that extends to the locus curve, that how well-defined extends to the locus curve.
Are you asking about this example here, or the zeta
I
here?
had a question before, but now it's partially asking. This will be a non-zero vector field on that locus.
This zeta, it could be 0 or not. Yeah. But in this example here, it's just the restriction of this zeta to the curve.
So what are modular leaves in this case of this Lie algebra? Is it just one leaf, or?
Yeah, that one is just one leaf, and along the line you have a non-zero vector field. Yeah, this is just the Poisson structure x bracket y is x, right? This has just
So there are two leaves. So there is an open one.
there's one-dimensional one and one two-dimensional.
Yeah. Okay.
And maybe I should do this example, even though I'm out of time. So just that everybody is taking part in this discussion, Pavel figured out already. So you have two modular leaves.
Because this Lie algebra is a model. For example, if you take P2 with the elliptic curve, then locally near every point of the elliptic curve, it looks like this Lie algebra, rule of this Lie algebra. And so
Near every point of what, you say?
near every point of this elliptic curve, it looks exactly like that. Because you
Of which
also drag it vanishing
which
to
elliptic
one.
curve? For P2, you mean?
Yeah.
Yeah, that's right. Yeah. So you have two modular leaves, but in general, for P2n, the vector field zeta restricts to this zeta here on the elliptic curve. So anyways,
The Poisson bracket has zero, first order is zero in this curve, right?
yes, that's
Okay,
right.
So
yeah.
that means it looks exactly like this Lie algebra. So if this Lie algebra has two modular leaves, then this will also have.
Yeah, this is right. Yeah. So I'm just saying that, and the thing that's, so this is all that can happen here. Actually, in general, you can make a statement that in codimension 1, not much interesting thing can happen. And I mean, codimension 1 and the degeneracy locus is just asking whether this modular vector field is parallel to the Hamiltonians or not. So, so it's equivalent to asking whether your degeneracy locus is reduced or not. In fact, if it's reduced, then you have just then you have finitely many modular leaves generically of codimension 1. Okay, so so X has finitely many even dimensional modular leaves. And then an even dimensional modular leaf, this is equal to a symplectic leaf where zeta is tangent. So our optimistic conjecture, we don't have a counterexample, is that the if and only if would be obtained by replacing finitely many modular leaves by only finitely many even dimensional ones. That is, symplectic leaves where zeta is tangent. I want to point out that in the homology case, homology version, this mx Ka should be, I say should be because this is only really interesting in the singular case, should be holonomic if and only if there are, so not Ka, but just mx should be holonomic if and only if x has finitely many leaves. Well, this is actually true. If and only x has finitely many symplectic leaves. So in my work with Pavel, this is with Eddinghoff. My work with Pavel, we proved the corresponding if and only if for the symplectic leaves for this mx. But if you replace it with the complex, this hasn't been written down. Basically, the reason why we have this difference is that Poisson Co Homology can be thought of as Poisson homology of x with coefficients in, I guess, the anti-canonical bundle. So kx minus 1. Right. And so the point is that from this you get the modular vector field. If you look at the Poisson vector field corresponding to your Poisson module, you get the modular vector field. So this is why you have the asymmetry between cohomology and homology. But for cohomology, you should have finitely many modular leaves of even dimension, and for homology, you need to have finitely many symplectic leaves.
So I didn't say, what is not written, you say?
For the singular case, we have not written anything with Brent Pym. I haven't written for a singular case, so nothing about the entire Poisson homology and cohomology in the singular case.
No, but this statement that homology is.
This statement is with you.
X is holonomic.
This statement is with you. We proved that.
But is it? It's not in the paper, right? Or
I think we wrote that. Yeah. Okay, I'm probably out of time, so I'm sorry. So let me just tell you what I didn't say is that in joint work with Pym and Matchevuk, we are going to explain that this conjecture holds if you have a normal crossings divisor, and you can actually very nicely describe what the Poisson Co Homology looks like in terms of the stratification that you get from log vector fields along the different components when you have a normal crossing divisor. Okay, sorry I ran out of time there. Thank you.
Questions?
Can I ask, so you discussed this non-canonical isomorphism and
Mm-hmm.
non-canonical isomorphism is associated with gradient, and there was this filtration by the order of Paul. Is it related to Hodge theories?
Yes, yes, I think so. So what I think is true. So first of all, we have this definition. You can have different ways you can define this. You can define this using this push forward of this D module, so what we call Poisson Theorem homology, or you can do this filtration I said using orders of vanishing, and those are only conjecturally going to give you the same thing. We haven't proved this statement that they give you the same thing. Now, there should be another way to do it. If you take, I was discussing this with Carl Mautner a week or two ago. I think there should be another way to do this. If you take, I think if you take the nearby cycles of this deformation, so generically we have a deformation of your symplectic cone, which is smooth and affine, and so generically this D module will just be the canonical D module there. If you take the nearby cycles along this deformation, I do think that the mixed Hodge structure there should be closely related to this filtration. At least this is what happens in my work with Pavel in the case we don't have a symplectic resolution but of just surfaces in C3. This turns out to be the case.
So this filtration should be the same as Hodge filtration for this family.
This nearby cycles, yeah.
Huh?
We proved this for the case of quasi-homogeneous surfaces in C3, but those generally don't admit a symplectic resolution. So only the Duval singularities have a symplectic resolution there.
Okay. Any other questions? Okay, let's thank Travis again. So, lunch break and we reconvene at 1:45. Yes, so still, if you have not signed up for dinner but you'd like to attend, you're welcome to do that, and you can still